Now we're going to talk about stresses and strain. First, we're going to talk about stress first, and we're going to go back to some real fundamental definitions, and we're going to really get into some engineering mechanics here right now. So the whole goal of this one is to, when we're done with this, we want you to be able to describe correctly label and use the of course, most appropriate geotechnical way of describing stress in 3 dimensions and properly label a tensor. We're going to talk about this concept of a tensor. I suspect the structure guys already know about tensors. And if you don't tell me about it, because I don't want you. Then I have to tell your professors that you don't know about tensors, and they're going to get all upset and everything. So, but let's start very simple. We got a point O. That point O is on a plane, and we're going to surround it by a certain area, a little elemental area, and we're going to call that area, give that area a unit of 1 because dividing by 1 is an easy thing to do. But it's a finite area. We're not talking about an infinitely small. We're talking about a finite sized area with 1 unit of area. And then we can have some people, I'm just going to call these forces acting along this area. Theoretically, if I did this, I would be drawing, let's see, do this right. I could draw this as, a stress distributed all across this area. We're just going to use one little area because drawing lots of arrows is hard. But the stress in that area is this total force over there, P, divided by the area, which is 1, so we're just going to be P. That's why we use an area of 1, because dividing by 1 is easy. So that's the concept. And this could be, we call these tractions. If you read engineering mechanics things, these are called tractions. But it's got some angle to the to the plane, and then in order to define it, we've got to have some axis system. So we'll pick an axis system. This one I'm going to just call it A, B, and C. So it's arbitrary. We normally pick the axis system. So 2 of the axes lie in the plane, and 1 is normal to them, because that makes a lot of sense. It'd be kind of silly to draw an axis system that wasn't that way. And then when we do that, it'd be useful to devolve this stress into its components in those 3 principal directions. Well, I shouldn't call them principal directions. We don't know that yet, but those 3 directions. So the first thing we're going to do is we're going to separate that vector into its normal component to the plane and that part that is parallel to the plane. And that normal component we're going to call the normal stress. Let's see, I think I want to go to the next one. We're going to call the normal stress there sigma. And then the A denotes the plane on which that's normal to. So that's our standard notation. Sigma A means that normal stress that's normal stress that's normal to the plane A. If it was sigma 1, it'd be to the plane 1. Sigma X to the X plane. That's our notation. That component of that stress that is parallel to the plane, we call tau. It's a shear stress. We call it tau. That's our notation for it. And we would say tau A because that's the component of that stress parallel within the A plane. It's actually in the A plane. The other one's normally A plane. This one's actually in the A plane. Well, the next thing we really want to do is we want to devolve that shear stress into the 2 components of the 2 axes that we're interested in. So we're going to have 2 shear stresses from this stress, and we're going to designate those as, for instance, tau AB. That's going to be the shear stress on the A plane. That this first one is the A plane in the B direction. So when we say tau, it's going to have 2 subscripts. There's going to be a first subscript and a second subscript. The first subscript is always going to refer to the plane in which that shear stress is acting. The second subscript is the direction. This is not a universal description. I'll show you some other ways people describe these right now. So any traction acting on a plane can have 3 components. It can have a normal stress and it can have 2 shear stresses. Obviously, any one of those 3 could be 0 at any given time, but there are still 3 components. All right. So this is I've given you a little SketchUp model. One of the other things, I find it convenient for some of these 3D things to give you SketchUp models, which you can draw and manipulate and spin around and look at. And I think I forgot to load SketchUp on my new tablet, so I can't sit here and spin them for you today. But I'll do that sometimes when stuff that's 3D is kind of hard to visualize. I think SketchUp is a really nice way to do that. So I've given you this. I think I did. Was it there? Did you guys see this? Did I load the SketchUp model, or did I forget to do that? Yeah. I'll look at it and it'll be up there tomorrow sometime. So let's just take our elemental cube dx by dy by dz, and there's my axes here. Here's the, this is the proper way to do things, by the way. Z is always down, right? And if Z is down and you want to have a right-hand system, then this is going to be x and this is going to be y. So this is the sign that we use for stresses is that compression is positive, right? Tension is negative. That's because tension is a bad thing, right? Tension, it raises your blood pressure. When things get tense, you need to have a beer, you need to float in the pool. And in the pool, you dive down to the bottom, there's a little bit of compression, it feels good. So clearly, God meant for compression to be positive and tension to be negative. So that's obviously a lot of a joke, but in fact, the engineering mechanics text I told you to refer to is going to have the opposite sign convention in it because it's an engineering mechanics text. And you know how this is, that there's just a few people in the world that really know the truth and do things right. Just ask anybody. Ask the Israelis, or ask the Egyptians, or ask the Southern Californians or the Northern Californians. Right? So this is the same thing. So the geotechs really know the truth here. All right. Tension is compression is positive. Tension is negative. There's a concept that helps you. The next one is harder. The shear stresses are much harder to figure out. But a concept that will help is with this concept. It helps to have the concept of a positive plane and a negative plane. So a positive plane is where the positive compression, the positive normal force, is in the positive direction of the axes. So by that I mean so let's look at this plane right here. So a positive plane is a plane where the positive normal stress acts in a positive direction. Okay, so all these normal stresses shown here are positive, right? They're all clearly compressions. We don't have any trouble with the signs for normal stresses. Tension is positive, compression is negative, and you structures guys just have to stand on your head. But the shear stresses are going to be a problem. So let's get this definition. Is that a positive plane or a negative plane? Okay, that normal force is positive, yes, right? And what direction is that? It's in a z. Is it acting in a positive z direction or a negative z direction? Positive z direction. That's a positive plane. Okay. What about? Let me change colors here. What about this one? It's a negative plane. That's a positive normal force. It's a compression, but it's acting. That's an x force, but it's acting in the negative x direction. That's a negative plane. And similarly, I'll just keep the color the same. That's a negative plane also. That's going to help us define our shear stresses. Okay. So now so the compression is positive. These are all positives. Okay. Now we have shear stresses. All right. This first one I'm showing you is tau zy. So it's tau. It's a shear stress. Z, it's acting within which plane? The z plane. Notice that this is a z plane. In other words, this plane right here, the normal to this plane is in the z direction, right? The normal is in this direction. It's a negative z direction, but it's in the z direction. And it is acting this particular shear stress is acting in the y direction, so it's a tau zy. All right. Similarly, this one is tau zx, and I can go through all of these and give the right label. So that's the labeling system. First label for shear stresses is the plane. The second one is the axis direction in which it acts. Now the question is, which of these are positive or which of these are negative? Now we got the symbols right. Now we got to get positive and negative right. And this is really confusing. So so these are all. I have shown in here in this particular. These are all positive shear stresses. All right. So there's two ways to think about it. I didn't make you write these ones down because they're really confusing. So. Maybe the better way to write it is that if it's a positive plane, like we just defined positive and negative planes, if it's a positive plane, positive shear stresses act in the positive axis direction. If it's a negative plane, positive shear stresses act in a negative direction. So, these definitions, although very wordy, are correct. If the direction of the compressive normal vector is in the positive x, y, or z direction, that means that it's a positive plane, right? then the positive shear stresses point in the positive directions. If the direction of the compressive stress vector is in the negative XYZ direction, then the positive shear stresses are in a negative direction. Or the way I like to think of it, it's a positive plane, which we define. Everybody kind of got that down. If it's a positive plane, shear stresses, positive shear stresses in a positive direction. If it's a negative plane, positive shear stresses in a negative direction. So this is one of those cases where two wrongs do make a right. You know what your mom told you. There's another way to think about it. So this is the engineering mechanics guy talking. If the unit normal vector out of the element is positive, then the positive shear stresses are in a negative direction. If the unit normal vector is in a positive direction, then they're in a negative direction. Those are saying the same thing. One of them is engineering and mechanics talk, and it's shorter, and the other one is English, and it's longer. Okay? So if you're a little bit dicey with this, and you may be, you should practice a little bit. So we have these 9 components to it. Now, notice that what we're really talking about is the state of stress. When we talk about state variables, that's what we're really talking about. This is a state of stress. So we have 9 components to this state of stress. This is, and we put them in a matrix. This is really, mathematically, this is a matrix. It's called a tensor. That's just the name we get to it. There's some theories about tensors, which we're not going to get into, but we call this a stress tensor. This is the notation we normally do. Down the middle of the tensor, we have the normal stresses. Down the middle of the tensor, and then on the off-center terms are the shear stresses. And we usually start X and then Y and then Z, and then you just match these up. So sigma in the Y direction, this is, if you want to think of this as the X row and the X column, and the Y row and the Y column in the middle, and the Z row and the Z column in the bottom, so that the shear stresses are just labeled with the row and column. So the tau XY1 is in the X row and the Y column, and the tau Z XZ1 is in the X row and the Z column. And I said this already, our normal stress is down the middle. Okay, this is another, just to show you that there are other ways to write this. The engineering mechanics guys like to write why should we have different terms for different components of the stress? There's no reason to do that. So you will see this notation a lot. It's a very common one for theoretical engineering mechanics folks to use. They just use sigma for all stresses. So a sigma XX is X plane acting in the X direction. So those are normal stresses. We don't like to do that because there's a big difference in behaviors between normal and shear. So we like to separate the notation for normal and shear. But you will see this. So if you see this notation, it's kind of more elegant in terms of, theoretically, because everything's got 2 subscripts, and so there's some mathematics about it that make it a little nicer, and you'll see this in programming if you've ever looked like in the guts of programming codes, because then everything's got 2 subscripts, and yada, yada, yada. So, but it's the same thing with a different language. We won't use it, but if you do see it, don't freak out. That's what if you see somebody using double subscripts and everything, you see sigma xy. That's for us tau xy. All right. Well, we don't really have 9 independent components. There's some relationships just from statics that give us relationships. So now I just want to look at one plane through here. We're basically here looking at a z plane. So I have the sigma y and sigma x, and we're going to sum moments we're going to use moment equilibrium to show us what's going on here about the point A. So if I use moment equilibrium about point A, then it's got to be obvious real quick that none of these normal stresses have any moment, right? Because they all act through A, so they're gone right away. So right away we can take all the. Let me change my color here. Right away we can get rid of all the normal stresses because they're not going to have any moment. So the only components that are going to have any moment about A are the shear stresses, right? So the shear stresses, I'm going to start adding up the shear stresses. The first shear stress is tau yx. So that's yx. That's this shear stress, right? It acts along the length dy. if I assume this thing is 1 unit into the board, so that's a shear, I'm trying to sum moment, right? I can't sum stresses, I got to sum forces, right? So that shear stress is tau x times dy, right? I'm sorry, this is the dy is the arm, I'm sorry. I am summing stresses, but the areas are the same on all sides. Sorry, I misspoke, right? So this is I've got tau yx here, and I've got tau yx here, times the moment arm there is going to be dy. Sorry, thing is jumping ahead of me. So the other component is going to be tau xy times dx, and so that's going to tell me that tau yx has got to be equal to tau xy, and so when I look at these, the stress tensor, these shear stresses in the if you mirrored this, if you reflected this across the axis, the shear stresses on the opposite side have to be equal in order for moment equilibrium, right? So tau yx has to be equal to tau xy, tau xz has to be equal to tau zx, and so when we do this, we don't really have 9 different components in our stress tensor. There's really only 6. And so for a bunch of you that's review, and for a bunch of you that's should be pretty simple, I hope. So here's the quiz. So the quiz is to write the tensor now for this set. So I've given you a state of stress, I've given you directions, I've given you magnitudes. So I would like you to write the tensor. I'll give you a couple minutes to do that. It's a good exercise. We'll most of us will get some of it wrong. So if you want to talk to a partner, find a partner. But let's take a minute and write the tensor. All right, let's see what we got here. So this is the correct tensor. Let's look at this carefully. So this is sigma x, right? So here's our x direction. That's 25. That's in a positive direction, right? In the y direction, this is the y direction here. The normal stress there is 30, and we have 30 there. That's positive again. And in the z direction, we've got 10. Again, it's compression, so it's positive. That's the easy part. Okay, so let me change colors here. So this 8, which actually appears, in 2 places. So let's look at this one right here. So this is acting in the x plane, right? So this is a tau x. That's this. And it's acting in the y direction, so this is tau xy. That's the correct place. Now, how do we know that's 8? Well, is this plane here a positive plane or a negative plane? It's a negative plane. And is that shear stress acting in a... So in this case, negative is positive, and positive is negative, right? Is that shear stress acting in a positive direction or a negative? Is it acting in the positive axis or the negative axis? It's in the negative xyz direction on a negative plane, so it's a positive shear stress, right? It's a negative plane, so this is we're in negative land. It's acting in a negative, it's pointed in negative direction, so it has a positive magnitude.
Why is it a negative plane?
It's a negative plane because this shear stress, this normal stress, is that a positive 25? It's positive. It's compression. It's positive, right? But it's acting in the negative xyz direction, right? Yeah. It's confusing. Don't get me wrong. It's confusing. Everybody sits there and nods their head until they try and do this, and so it's confusing. All right. And similarly, if we look at the 17, let's see. I think I can do this right now. Here's the link on the slides. All right. If we look at the 17 here, all right. This is again. It's still a negative plane, and that's acting in negative direction. So that's a positive 17, right? And notice that it's positive there. And we could come over and look at the 17 here too. Let's look at the same. These are the 17s that are coupled together. Right? Look at this 17. Right now, this plane right here, is that a positive or negative plane? That's a positive plane. And notice that 17 is acting in the positive x direction. So it's positive plane, positive orientation, positive value. The 17 here is, it's in a negative plane, has a negative orientation. Maybe that's a better way to say it, orientation. Negative orientation, positive value. I just discovered a better way to explain this. It's their orientation. Okay? And then finally, the 22. Let's take a look at the 22. So here's our 22. All right, so this plane is a positive plane or a negative plane? It's a negative plane, but notice the 22 is acting in a positive z direction, so it's negative. And you can check it on this. You can check it on this plane. You'll find the same thing. We have to follow this convention. It's critical that we all do this right. If you don't do this right, you code up your codes. Everything's wrong. So, and it's not intuitively obvious. It's an arbitrary definition. It's not that simple. So go practice these and get them right. All right. Cool.